If there's any organizers in the room, appreciate the opportunity to speak here today. This is a project that I took on borderline individually and have sparked quite the interest within NASA now. And so I'm here to learn a lot, but also to kind of give people an idea of what it looked like and the reasons why we looked at GraphQL internally at NASA. So we'll go through a couple of things today, mostly an overview of what we're even looking at, so Earth data, science data, what APIs we have available to us and what they do, the challenges that we face with those APIs, and then how GraphQL helped us streamline the use of those APIs. And then assuming we have any time at the end, we'll go through some examples of where we're using it today. So what is Earth data? Is a slide that we like to kind of show what we're actually working with. So when I say I work for EOS, Earth Observation Systems, it really means all of these satellites combined with aircrafts and ground stations, and all the imagery and the data coming from the instrumentation attached to all those different vessels. There's kind of a timeline associated with a lot of these. You can see the launch dates, and we have future launch dates as well. Historical launch dates are some of the data I have here today. The future ones are the things that I'm currently thinking about in my quest to GraphQL all the things for a number of reasons, and I'll touch on those in a bit. How do we store and access the data that comes from all these systems? We have 13 today distributed data centers, we call them DACs, across the country that are responsible for storing the raw data and the expertise that comes in the form of human beings that are scientific and experts on that data. At those facilities and amongst now our migration to the cloud, we store the raw data files that come down. Those are anything from small imagery to HDF or other scientific files that are used for the purposes of science. As of 2022, the raw data files accounted for about 72 noted here, petabytes of information, again, distributed across those different data centers. That information is vital to our research and discovery of climate information and information about our Earth. 72 petabytes is a lot of information. However, with the launch of new missions, we're estimating somewhere in the range of 600 petabytes of information will be at our disposal by 2029 that we'll need to be able to search. We store all the metadata associated with those underlying data files in an API or a storage mechanism called the CMR, which is the Common Metadata Repository. We ingest all those pieces of metadata in a couple of different ways. The native formats can be anything coming from the DAC. So oftentimes a particular aircraft or satellite or instrumentation on a satellite stores its data in a particular way because of the instrumentation's, what it's retrieving essentially. So it could be something simple, it could be something more complex. ISO being one of our larger files, those can be 20 to 50 megabytes individually just in metadata. But it's all based on the mission and the instrumentation. We have about 1.5, I was telling some folks I had to write these slides a long time ago for government legal purposes and get them approved. We've surpassed this now. We're nearing about 2 billion metadata records that our GraphQL implementation is responsible for searching and finding relevant information within. So when we look at the CMR and all the data that's stored there, there's a whole bunch of different pieces of it. And how the users and the scientists and our own applications access that is through different APIs. And so what APIs do we have available to us? The core APIs we have 3 of: ingest, search, and lastly, access control. I'm not going to touch on access control today, but it does introduce a fun quirk and or roadblock, if you will, into GraphQL, where everything we do is very granular in terms of what you can access. Unfortunately, this is mostly historical API because all of our data is free and open now, but we have to remain true to these old ACLs. Then we have a couple of ancillary APIs that we currently use. Stack, so this is similar in a way to GraphQL, where the science community is looking for a particular API standard to fall back on for all of our machine-to-machine operations. So that's Stack, the spatiotemporal asset catalogs. That allows people to search for spatial and temporal information in a very known and spec-based way. Virtual directory and OpenSearch, less important, but just noting that we have additional APIs that are using data stored here. Ingest, which is the process of taking in this information from a satellite or an aircraft, writing the data to a data store, and then processing the metadata. We have come up with, as you maybe have heard a couple times today, metadata. As you go to different earth science conferences or science conferences in general, you'll hear people talk a lot about metadata formats. It's one of the most painful things that I go through. Every conference I go to, someone always says, I really like the fact that we have a metadata format. It didn't work for me, so here's mine. And now we have 4,000 of them. We have our own in UMM. UMM is NASA's version, but it's been vetted by a vast majority of the scientists in the neuroscience community, and most everybody is all about using it. So we prefer that method for ingest because it captures all the pieces of information that we need for our entire ecosystem of applications and APIs. All the UMM models are backed by a JSON schema, which again go through review amongst the community and allows us to ensure that we're not missing anything for new missions, old missions, or particular fields of science. This does all the validations and the known fields for our different applications, and the fact that the community agrees upon it is super important to us. As part of that, we version those schemas, and that's great, but ultimately the API itself isn't versioned. And so we had to build in the ability to request a particular version for the UMM record, but the API just has it as a query parameter, which works, but isn't great from an API perspective. But it does allow us to migrate the data. So if we introduce a new version and there's some changes we have to make, we're able to make those on the fly or during ingest. We also allow people to query for the older versions. Non-UMM records, so these are, like I said, ISO or ECHO or DIFF. These are old XML file formats, larger in size, more widely used previously. We store them as raw files and we translate them on request. So we'll talk about that in a bit when we get to the GraphQL implementation. So search, this is our big one, and this is where I'll be spending most of my time today, and that's where GraphQL lives. So we have multiple request formats. So rather than having different endpoints we use, instead we use formats. This was kind of made more popular, if you will, around the Rails time, where we could slap on XML or JSON or HTML at the end of a particular URL, and you would be delivered the correct format. The developers at the time of this application, which was about 10, 11 years ago, decided to do the same thing. So we have JSON, we have UMM, which we just talked about a minute ago, ISO, ECHO, DIFF, there's a whole slew of them that are available. The challenge that we have with this or the feature is that each one of those support a different type of request parameters and capabilities. And it was mostly because of the fact that we're making some assumptions about what was ingested and what that user is expecting to be able to do with that data. Whether or not that was a good thing or not was up for debate. I think the most challenging part of this API and continuing to the GraphQL implementation challenges are the fact that we have a requirement that every single query, or 95% of queries, have to be returned in less than 1 second. That's tough at volume. So outside of having to return in 1 second, what are the challenges that the current APIs pose for us? Search parameters only being available in one format is super annoying. So if I'm a scientist and I know that I need to request a particular format, but in order to get the data I want, I need to be able to provide a certain request parameter, but it might not be available. That's super painful. The keys that I'm requesting aren't always available. So the UMM is a JSON schema, and all that data is stored in one JSON structure in a row in a database someplace, and it comes back as a full thing. Now, we've optimized particular keys on the JSON side That might be a smaller piece of information. It might be a concatenation of a piece of information, and it's available on the other, faster endpoint and isn't available from the one that I'm using, which might require that I make 2 queries. The JSON endpoint, again, is optimized. It's stored in a cache. The UMM is not. It's in a database. And so those fields that I'm looking for might be the same thing, but the data they contain is slightly different. The more verbose version is going to sit in the UMM, and the optimized version is going to be over in JSON land. Outside of the fact that they contain different data, there might be just called different things. Concept ID, because UMM, they're called concepts. We have a collection concept, a granular concept. Over in JSON land, they're just ID, because it is. We have redundancy because of the fact that we can't change, like JSON, we can't change and remove keys because our active scripts, and a lot of our data is used for real-time response for natural disasters and emergency response purposes. If we just were to change a key, we might put someone in danger. So instead of changing the keys, we just make another one, and we reference the old one. Someone wanted it called title, and it was called abstract title before. We just have both now. And users never know which one is supposed to be used. I have data set and title as my example. Determining the number of results that come back from the APIs is also different. And so when someone's using a machine or a script to parse through results, because we often do the same exact thing there, where we have someone's looking for the most up-to-date data from a particular satellite, they're just going to ask, hey, what's the data from today and today? And oftentimes, we need to page through that. But depending on what endpoint you're going to, it's different. Facets, a big one, right? You think facets, Amazon. So I am the author of Earth Data Search, our flagship search product. Among myself and 2 other people rewrote this recently, where the facets are super useful for users searching in our map interface. Only available in JSON, not in UMM. Not super great. Additionally, we have a lot of performance issues. This is kind of an ongoing effort or thing that we're working through today. From the server side, we have a couple of things to note. JSON is an elastic search. It's quite fast. Database queries are required to get the UMM records out. That's not great. Ingesting native formats and having to translate them later. Again, ISO records can be 10, 20, 30, 40 megabytes. Having to do that on the fly, pull them into memory, and translate them on response, and keep it in less than a second, super challenging. We end up with redundant and duplicative queries. So not only from a client side, but also from the server side, we have people making 2 queries and putting unnecessary load on the servers and on the client side. Paging has been a huge issue where, depending on the implementation, we've changed it 3 times. I'll go through this a little bit later. We were bringing ourselves degraded service events based on the way that we were paging and offering paging through our APIs. And again, changing that and expecting users to change the new way was super challenging because you had to change the query parameters altogether. From the client side, the size of the response was a big deal. NASA has made a big push to switch to the cloud, so a lot of our development efforts are now moving into AWS. And for all of our APIs, like, why wouldn't we use API Gateway? Well, API Gateway has a 10 megabyte maximum payload size, which seems like a lot and is a lot until you start bringing in geospatial and polygons into the mix. I can give you a polygon that will be in 10 megabytes in no time. Also 30-second timeouts, but again, not that big of a deal because I'm required for 1 second, but we still have issues sometimes. The volume of the queries was double what we always needed. So all of our clients knew we needed something from both sides, and the clients were just making 2 queries every single time outside of our scripts. Maintenance, overhead, and institutional knowledge of how and where to find this information was also very painful. So if I'm a client, that could be an application with a NASA, that could also be a scientist out in the field, it could be an emergency response system itself. Given that the API is not versioned, I can't, as a developer, make changes to this knowing that I'm very likely going to break something. I also don't have the ability to ask these people for information because I don't even know who they are. There's no requirement to identify yourself in an open API, and if you're a researcher out in the field, you might not even be accessible at the time. So I can't make those changes. And I think that last piece about the usage being unknown is the most important part, because I can never have the user query or user survey that a lot of people reference all the time. Like, well, would you mind if I did this? I could ask, but someone's always going to come back and say, what happened? Why'd you do that? So given all these challenges, what and how did we do it to streamline the ability to access those things with GraphQL? So I'm going to pretend for a second that I'm a researcher, and you guys can all come along with me, I suppose, using Modis, one of my favorite instruments that we have at NASA, mostly because it uses the term moderate, which is kind of how I feel about most things. I'm going to do a lot of moderate effort. You can see what Modis is capable of, though, given its moderate effort below. It is a very important tool. In fact, it exists on 3 separate satellites because of how good it is at its job. If I'm a scientist wanting to access information, though, it's super difficult. So let's play pretend. We're going to be scientists today. I want to find data collected by Modis on board the Aqua satellite. So typically a scientist is understanding where and what satellites and or vessels they're looking for and what Aqua is doing for them. So in my very simple search to do some science today, I'm going to be looking for a few pieces of information. I want to know the unique identifier. I want to know the title of the data that I'm looking for, the DOI, because I'm going to cite it eventually. This is our digital object identifier. And I want to ensure by seeing the platforms that it was available on. And then, for my purposes of my client, I also want to know how many records there are, and I need the ability to page the information. So how do I do that? Today, JSON. This is our one endpoint. So I'm making a pretty simple REST API call. I'm doing a post here just for the sake of showing the arguments, not in a long string. So I'm going to include my facets so I can provide that to the users, and I'm going to say, give me the platform Aqua. Now, when I make this request, this is what's going to come back to me. Now, realize that both JSON and the UMM response is a large payload I don't have the ability to restrict any of the keys by, so I'm cutting out just the piece of information that I need today for this purpose. If I need to page it, you can see back I have some response headers. That's for my hits, which is how many records there are, and my search after, which is now the preferred means of searching and paging through this information, which is the third rendition of this effort. But that's not all the information I asked for. Like, where is DOI, for instance? Where is the, no, I have title, but I don't have DOI. Now I'm going to UMM, I'm going to make the same request. I don't have to provide facets because it doesn't offer facets. So I've got my facets, I've got my number of results, and you can see my headers come back without the number of results, but I do have the same header for paging. My response now, though, has the number of hits right inside of it. It also has timing information. That's pretty useful. And my DOI is now available to me as well. So with these 2 requests, I have both of the pieces of information I have, but you can see how the information that came back is not only different, but it's disparate in the fact that I can't get it from either one of them individually. And I did note in the bottom the size of these responses that I didn't mention in the last slide, but relatively small, but still more than double when it comes back down to the GraphQL side. When I do this in GraphQL, you're all relatively familiar with the query language itself. So I've done the full query from both endpoints, and my response now can include both things. So from a user perspective, I don't have multiple ID columns. I don't have title and something else. I have my platforms available to me, my DOI is available to me, my count, and my ability to page using cursor is all available to me. And my response, you can see, is even smaller than just the one previous one. So ultimately, what I tried to do with this was obfuscate all this stuff, which was by design. I don't want the user to have to know what's going on. Based on the fields the user has requested, can I intelligently determine where to fetch the data from? That includes one being more performant than the other, not just the keys being available on the other one. At this rate, users no longer have to know that the formats even exist. They just know that the GraphQL endpoint exists and the documentation is available to them. It allows me on the back end to prioritize the faster endpoints and formats, but also understand that the data that's coming back could be different, and one of them might be for historical purposes and doesn't need to be returned in an API. I can also normalize and or make more consistent the queries parameters and the response fields, and the user doesn't have to know that it was ever aliased. Abstraction is one of the most important parts of this for me. allowing changes to our underlying APIs without the clients having to make any adjustments. The biggest one was our paging, but again, having a field researcher or a script or a system that's going to tell me immediately about an earthquake is super important to not break. Now I can make a change, make it more performant, change something in the underlying API, completely swap it out. No one has to even know. And generally, as we've heard many times today, all of our underlying APIs are just HTTP requests today. We have moved some to Graph Database directly. We're able to now make direct calls to Graph Database for much more performant requests. We've been able to introduce new services entirely. So where one application used to do two things, we're able to pull out one of those things from a hyper-performant version of that thing, and the users didn't even know that was happening under the hood, which in turn allows us to retire old services, which we have. Just about 2 months ago, we retired nearly 1 million lines of code from an old system within NASA, which was party-worthy when you had cake, because that's the only thing the government would budget. Best practices. In the scientific community, best practices, specifications are king. And so by being able to lean on something where I can tell people this is the agreed upon standard versus this was NASA's opinion, it's much easier for me to make that argument. They don't care about NASA's opinion, they care about science and the community. It doesn't matter who you are. We had 2 versions of our ability to page to our application that again caused degraded service events within our API, which was a huge problem. And so we ultimately had to change them. Now we were able to do that 2 times. We're in our 3rd rendition, but we didn't have to change any of our applications or our client code. We had what we call deep paging, which is just give me the page number. That was atrocious. We had scroll sessions. It was slightly better, but very painful to use and still resulted in that, in degraded service events. And we landed on search after, which is cursor-based paging. When we do that internally, the way that I was doing it is I have a base64 encoded string, which is the cursor, and a base64 encoded string doesn't have to be just a string of text. A string of text could be a stringified version of a JSON endpoint or a payload. And so what I did was I stringified a JSON payload from both of the endpoints, and so I'm able to simultaneously query both of those endpoints with a single cursor, and again, the user doesn't see it, which was phenomenal. So ultimately, GraphQL, what did it do for us? It reduced and eliminated both response and parameter inconsistencies and removed the user from having to know what and which ones to use and when. Also, the fact that we even had multiple APIs and that they were supposed to use one versus the other. We have future-proofed much of our APIs because of the fact we have this abstraction layer now. We can change underneath, we can add new things, and as we go through what NASA is calling the unification, web unification effort, and they're expecting us to change our web applications, all of our DNS, and everything related to our underlying APIs and systems, we can now do that, and no one will feel that pain except for us, and that's okay. I think we have, it's currently 4:07, we have just a couple of minutes. I'll just I'm gonna breeze through a couple examples, and in the event there are questions, I can get those real quick. Earth Data Search, again, the application we rewrote, which has been the thing I've worked on for the most of my time here, is not 508 compliant. We have to have a 508 compliant version of it, so we wrote this thing called Access, which is the 508 compliant version of that, and it has these landing pages on it for each one of our concepts. This is a single GraphQL call, but each one of these tabs down here is a separate call. It's a separate concept, and the user doesn't know that. And we're able to use this now as a React component or an exportable widget that we use across different platforms. CMR has static landing pages for all of its data as well. This is just, as you can tell if you look at these two things, identical. It's using the same widget. So it's ultimately making one GraphQL call across multiple applications now. CMR Stack, this is our Stack compliant API. But this is calling GraphQL under the hood. So rather than doing a whole bunch of redundant work to gather the information it needs, it just makes quick queries to GraphQL and returns in a slightly different format to appease the scientists. And then Earth Data Search. This is a massive application. This is making some relatively large queries to GraphQL with pretty deep nested queries. And it has cleaned up our entire code base. Like, we've removed thousands of lines of code and just probably 20 different REST API calls in this application, and it's made it very, very clean. So I left myself a whole minute. If there are any questions, I'm happy to answer those. But otherwise, thank you so much, and I appreciate the opportunity to kind of tell you guys the process we went through. Go ahead. Nothing. All right. Yeah, go ahead. Yeah, sure. Unlikely. So my purview is Earth science, which is Earth observation systems. All of our API, we've wrapped only CMR thus far as part of the web unification effort that we're going through currently. Sorry, the question was, have we introduced GraphQL essentially to any of our open APIs today? And the answer is no. This was essentially my attempt to handle those challenges I was referring to, and in the process realized how powerful GraphQL actually is, and I'm currently making the case to do just that. So the question is, what has been the reaction of the users? Mixed. I think that the initial reaction from most people was definitely, I'm not doing that. However, I've presented now, this is like the 4th time I've presented this topic as a whole. I tailor it, I've done it 3 times internally, and each time someone who has presented kind of some pushback initially has come up and said, oh, now I see why that might be useful here and there. And it's really just like, and I think everybody who's in the camp of having to explain this to someone and justify it, there's a use case. And I'm not just out here trying to change things, you know? And so until you can kind of hit that one spot that is meaningful to that person, you're not gonna win them over. But it's coming around, honestly.
Are you aware of all the agency data GraphQL might be Abbott? Have you heard of all that?
I'm currently undergoing, we're re-architecting the entire system that ingests and makes all this stuff searchable right now, and it is in the discussion as a means of, because we have other contracts that we don't have control over, and so we can't tell them what to do. However, if we can make the case that we need subgraphs, and you know, if you can at least align to this, I don't care how you implement it, that might be more feasible, but I can't step in and do that everywhere. But that's the hope, honestly. Cool, well, thanks so much. I'll be around if anybody has any additional questions.